All right, all yours.
Great, thanks. So as Olaf mentioned, Connor and I are going to be talking about the Open Reaction Database today. And probably the most exciting bit of recent news is that Ben is here. So we just got a big grant from Schmidt Futures, which we're really grateful to receive, and will support our work. And one of the first things we did with that money is hire Ben. And he's got a lot of great experience, and I'd love to have him introduce himself briefly as our program manager and data evangelist.
Yeah, hi everyone. My name's Ben Deadman. So originally, if you detect an accent, I'm from New Zealand originally, but I've been over in the UK for about 14 years now. So my background is as a synthesis chemist. I've done a lot of flow chemistry in the past for my PhD, and then high throughput experimentation with the Center for Rapid Online Analysis of Reactions at RAW. So I guess that's my strong point, is in taking the synthesis, a bit of reaction engineering, device manufacture, and combining that with some data science. So yeah, I'm really looking forward to working with you more, working with the synthesis chemists, and kind of bringing the communities together.
Great, thanks, Ben. So stay tuned for additional news and outreach from Ben. We have a few exciting things that we're going to be able to do because of this grant, including things like grants to academic HTE centers for generating data that will eventually make its way into the Open Reaction Database. So I just want to give a brief overview of the database and the effort, and then Connor is going to do a quick demo of some of the tools that we have available to us and that we've built over the last couple of years. But the real broad overview purpose of the effort here is to provide a database to support machine learning efforts in things like reaction prediction, synthesis planning, and experiment design as well. And so a number of things have been built and worked on in order to enable this goal, including the development of a schema, which we'll show you, and which Connor's demo will go into more specific detail about how to populate the schema and use that. We also provide interfaces for browsing and searching the data that exists and that has been submitted. And the Open Reaction Database is intended to be truly open. The data is freely and publicly available for anyone to use, and we're working hard to encourage data to be shared that wouldn't normally have been shared in the past. For example, pre-competitive and proprietary data that especially comes from HTE sources, because we feel like this consistent data generation methods are going to be the best source of data for machine learning efforts in this area. So when we set out to design the actual schema, we started by asking a lot of people what they thought should be in a schema. We got a lot of feedback from our initial survey, which was done a few years ago now. We started this back in 2019. And as you'll see as I walk through kind of the main components of the schema, there are a lot of places to put structured data, exactly the identity of the reactants and the identity of the products and analytical data and things like this. But the schema is also very flexible in allowing unstructured data to be stored as well. And so in a lot of the places in the schema where you can put in very specific details, there's also generally places to put in arbitrary details in a free text format. And we made that decision very, very deliberately, and the choice of what types of data are structured and what types of data are unstructured is really something that will evolve over time. But we started out trying to make data structured if we felt that it would be useful for machine learning applications. So if it needs to be machine readable in order to be useful for prediction, that data tends to be more structured. And if it's something we're not quite sure how to use yet, or if structuring it is a real pain, then it's something that is more of an unstructured field. And one thing that sets the ORD schema apart from other types of schemas or formalizations of reaction data is that we're really trying to capture what actually happened in the lab, as opposed to say what the intent or design of the reaction was, or even a particular, protocol or workflow for automated synthesis hardware. So this is more, you could certainly imagine using the ORD to specify those things and to do design of experiments and things like this, but the schema itself is really designed around capturing what happened, regardless of whether or not that was intended in the initial design. So you'll find places where you can record temperatures and specific amounts of things that were actually generated, as opposed to always just what was intended. So the schema broadly is divided up into there's a reaction level, and then it's very hierarchical in terms of allowing different identifiers for the reaction, inputs for the reaction, information about how the reaction is set up and various conditions, lots of different places to put data. And one of the things that we've heard recently, you may have seen this new paper about the SURF descriptors that came out a couple of days ago. And so that's sort of a tabular format for handling reaction data. One thing that the ORD does, I think, is provide a lot of places to put data, and it's really intended to be able to support whatever data you might happen to have available, but by no means is every field required to be filled out. And so there are a subset of fields that are expected in order for a reaction to be a reaction, but a lot of the other places in the schema where you can put data, it's fine to leave them empty if you don't have that data available. And so I think of the schema as kind of a one-size-fits-all solution where you can put in as much data as you have, and if you need to put in, if you have additional data, there's usually a place to put it as well. So I'll go through at a very high level an example of a fluorination reaction, and I imagine Connor's demo will actually show you how this works procedurally. But if you imagine a simple reaction like this, broadly, the way that this would be organized in the schema is that you have a set of inputs in the reaction schema, and you can define hierarchically the different inputs, like the alcohol and THF and the sulfonyl fluoride and the base that you're using. And so one nice thing about the inputs here is that you can have an arbitrary number of them. The schema totally supports that. And the schema can be accessed both programmatically and through our web interface, so that you can iterate over these things and manipulate them regardless of how complicated the inputs of the reaction are. And then the individual compounds have different identifiers that can be added. You can put in Smiles identifiers, or if there's a name available, you can put that in, not required. And then we have places to put in amounts and different reaction roles. Again, the reaction roles in particular are not something that's required, because those are often relatively arbitrary designations. Same story kind of goes for the parts of the schema around the setup and the conditions. We have ways of specifying in a structured way the reaction vessel that was used, as well as the environment that the reaction was performed in. Same for things like temperature, pressure, and stirring, where again, we have the different enum fields to specify specific types. And if there's a type that you need to support that isn't in our enum, it's possible to define a custom type in every place where we have a structured enum field. And then for outcomes, since outcomes are usually only really understood in the context of both a product and an associated analysis, you specify the product and then specify one or more different analyses that were done on the product with measurements for that analysis, so that you can put in NMR data, or if you have LCMS data or other things that are added that as descriptors of the products, the reaction, they're all supported in the schema format. Let's see. As far as that's kind of overview of the broad schema, are there questions about that before I move on to kind of more technical parts about where ORD lives and things like this? feel free to ask questions also during Connor's demo where this might be more clear. So not only is the data in the Open Reaction database open, also the code that we use to define the web interfaces and to define the schema, all of these things live on GitHub at the Open Reaction database organization. We've also put a lot of effort into making sure that from a legal and licensing standpoint, the data is accessible. So the data itself is licensed under a CC by SA license. The code is under an Apache 2 license, and we have examples and tutorials available on GitHub and YouTube. We've invested a lot in refreshing our interfaces lately, which you'll see. So some of these examples and tutorials may be out of date, but it's one of the great things about having folks like Ben around now is that we have a little more bandwidth to keep those things up to date. And I'll shout out as well the great work of Michael Kennel, who's one of the CCAS software developers, who's really done a lot of great work to refresh our searching and browsing interfaces, which you'll see in a moment. And there's a lot more details about this stuff at the docs at the website. So I will quickly share the search and browse interface. Connor, you were just planning to do the editor, right?
Yeah, feel free to hand it off whenever.
Okay.
Your call.
But if you go to openreactiondatabase.org, you have the option of looking at all the data sets that we currently have. You'll notice right away that a lot of these data sets are coming from the USPTO grants database that we converted into the ORD format. And so you may have to scroll through a little bit to see things that are coming from other sources, just because this is such a large database. But once you find a database you're interested in looking at, if you click on it, it'll bring it up in our search interface, where you have the opportunity to search and filter based on different facets here. And if you find you can share a link to this particular search outcome, including all of the different search parameters. You can select multiple reactions and download them. And then there's a page for each individual reaction where you can see all of the inputs and outputs as defined in the schema itself. So if we look at the full record for this particular reaction, this is kind of the machine readable schema representation of what's going on. And we have it nicely presented here in this per reaction landing page. But now it's probably a good time to hand it over to Connor to talk about the other exciting aspects of the interface and anything I may have left out.
Awesome. Thanks, Steve. Go ahead and share my screen. Make sure to get the right window. All right. Yeah, so as Steve mentioned, things are sort of being revamped as far as the interfaces go. And so if you do sort of poke around the website, you notice things that don't seem like they're working the way they should, definitely just let us know. And by us, I kind of mean Ben, who provided his email kindly in the chat. And then we'll make sure that we create GitHub issues for these, or you can also open GitHub issues yourself. So Steve just sort of mentioned the sort of viewing data sets, browsing data sets. I'm going to talk a little bit more about the contribution process and just give an overview of the different ways of contributing and really the different ways of defining a data set in the ORD format. So if you sort of go to the ORD website, on the upper bar, there's a contribute button. I'm going to go ahead and create sort of a new empty data set. Clicking on this new empty data set, it takes me to now this sort of empty page. You can have a name, a description for the data set, and then of course you need to add reactions, right? So the main sort of units in the ORD are single step, experimental, synthetic organic reactions. And so if I look at an empty reaction, currently in the editor, and again, this is all being sort of redeveloped and redesigned, and we'd love your inputs for this process too, because we know we want to make this look a little bit more compact and more like an ELN. But right now, you're faced with this rather long form, which exposes a lot of the complexity of the schema that Steve alluded to. And just because the complexity is there does not mean all the fields are required. It doesn't mean that all this information is necessary. but it does mean that we want to be able to capture this extensive detail if that information is present. So on this empty page, you might notice right off the bat, we have 3 error messages showing at the top, and that's because we have this sort of automated validation going on in the background telling us what's required for a submission versus what's recommended for a submission. And so here you can see, well, the big errors are, this is basically an empty reaction. There's no input, there's no outcome, there's no source of who ran this reaction. And these are the things that at a baseline we require. So each entry, right, is made up of these different sections on the left that Steve summarized on the slide. Inputs to a reaction you can think of as either pure components or stock solutions, or things that are added to the sort of reaction vessel, which is again the unit of the reaction here. Inputs can have different names. Each input can have components that you add. Components, as you might expect, can have reaction roles assigned to them. Compounds can be defined by different identifiers. So we could choose smile strings if we're so inclined. We could instead choose to draw the compound using Catcher. If we'd like as well, it's also possible to do some little silly things. I don't know if you can see this sort of pop-up menu, but you can do some basic text resolving, and you can say, I want 1 milliliter, sorry, of 50 millimolar aniline in toluene, something like that, and it will automatically create this new input, which has the sort of corresponding amounts measured in moles, the solvents measured in volume. Now, again, the richness of this schema is trying to let you record a whole bunch of metadata. And this is maybe metadata that isn't so important for machine learning right now, but it's important for reproducibility. Maybe it'll be important for machine learning a little bit down the road. So this might include things like for a compound or an input that you're adding, whether you've done anything in particular to repurify it after sourcing, who you ordered it from, what the lot number was, or the catalog ID, if you're interested in adding that level of detail. You can also annotate sort of arbitrary data associated with each compound in case you want to sort of store pre-computed features or ligands descriptors with the data set as well. Or this could be QC data. So there's all of these ways of adding different information about the inputs. In the end, you can think of these as stock solutions or pure components that are added. We want to capture things like order of addition, order of speed, and so you end up with this rather long form that continues and continues and continues. So for the reaction setup, we might record that this was done in a vial, it was a glass vial, it was, like a 1 gram vial. I didn't use automation, but I did this in a glove box, right? And all of this information is things that we know to be important that we usually just put in unstructured text in supporting information paragraphs, but they're fields that we now capture in this structured format. I'm not going to sort of go through this full thing, but suffice to say, all the detail that I would hope could be associated with a reaction for the most part is able to be described here. Now, of course, there's always going to be exceptions. So for example, the ORD lets you specify 1 reaction temperature, but there may be a reaction that goes through sort of multiple stages at distinct temperatures for distinct periods of time. And so we do have these catch-all text fields where that unstructured description can also be captured. Reaction outcomes can be added. Multiple outcomes per entry are okay. And so those could correspond to multiple time points if you're doing a kinetic study. At each time point, you can annotate all the different products, all the different analyses that were performed, and all the different associated measurements and calculations like reaction yields that you might infer from the analytical data. Yeah.
So this is scary for me every time I've seen you present it.
Yeah.
Perhaps because I'm old and have no idea how to do anything. Is it possible to have an Excel spreadsheet where you can copy and paste things and import it directly into this? I think I've asked this before, but I have no memory of the answer.
Yes. So I will address the sort of spreadsheet use case in a moment.
Yeah, because that's how we run a lot of our, libraries and such. Yeah.
Yeah. No,
okay.
Absolutely.
Sorry.
I'll come to that. No, it's a good question. It's an overwhelming it's an overwhelming amount of fields and yeah.
I mean, for me, who's busier than hell, I would never be able to get past the first, part of it and get distracted. But maybe graduate students are not like me. That's a joke.
No one is like you, Matt. All right. I'm going to go ahead and actually skip to that sort of spreadsheet usage, because that is one of the more common ways that we see contributions be made. So what you can do, actually, while this is still sharing, so what you can do is, after you've defined a sort of single reaction, and so here's a reaction in the form that's been actually filled out, and so you can see sort of a summary at the top. You can see that we've specified amounts, we've specified identifiers with names, with structures. We have catalog IDs. This was bought from Sigma Aldrich. We have, this is a microwave reaction, so we've got all of those sort of details specified. What you can do at this point is you can download this reaction that you've just defined. That'll download it in this sort of like pseudo human readable format that Steve showed before. And at that point, you can sort of turn that single reaction you've defined into a template. So this is right now like a little bit of a manual process, and we're sort of working through more sort of visual on web app ways of doing this. But if we sort of take this template that defines a reaction, which we do have to go through the full oppressive form once to basically define everything that's associated with the reaction that's being held constant. But after we've done that, what we can then do is we can basically turn some field values into placeholders. And here we've just chosen to use $signs as the sort of separator variable that says, I want to basically turn the name of this component into a variable. I want to turn the smile string of this component into a variable. We do that for many other aspects of the reaction, all the way down to like the outcome. We turn the product smiles into a variable, and we also turn the yields, here it is, into a variable as well. And so if you've defined a single reaction, which yes, takes a lot of effort to make sure that you're incorporating all the detail that is relevant, then you can define these placeholders. And with these placeholders, you can basically upload the templates and a spreadsheet, and it will do the enumeration for you. So we're sort of more used to having spreadsheets, right? As you said, basically just record what's changed in the reaction. So each row is a reaction that we're running. Each column is sort of a different variable that we are varying in each of our experiments. And so you end up with this sort of tabular data. And so, yes, if you've got this sheet that defines basically what is varying, including the product smiles string or the name, the yields, things like that, all you need to do is define a single template reaction. And then you can sort of zip these together and enumerate the full data set based on your spreadsheets and that one template reaction. And that's also something that we can sort of help walk through for a couple of examples.
Yeah, so can I make a comment? Maybe this is to Ben, is having this interface perhaps looks more natural to organic chemists than the one you have on that other slide. So having this essentially as the template in the first case, where you press the top button, have pull down menu for solvents and all these other things, and let people drive it. I think it looks more like a notebook, electronic notebook.
Yeah.
So I think, honestly, Jamie and I were talking in the background here, is if you guys actually invented the electronic notebook that actually worked for this kind of purpose, that would probably solve both problems simultaneously. I think I did offer this advice 15 years ago when we started this discussion, but
no, and we heard you, and then we put it in the grant, and so we do have dedicated financial support for that.
Yeah, that's awesome, because I think that's the solution and to these problems when folks like my lab, who doesn't use electronic notebooks because hate them, can maybe adopt an electric notebook that's directly tied to submission, because that's what we want to do.
Yep, exactly. No, it's terrific. And I think I heard that Jamie volunteered to have a meeting with Ben to talk about his ideal interface. Is that?
Yes. I volunteered, Jamie.
Well, there we go.
But I think a few of my people, actually more than one, right? Because I have a
Yeah.
bunch of people running reactions in my lab. And then connecting it ultimately to perhaps feature space as well is something we talked about a long time ago.
Yeah, absolutely. And I think this better sort of integrating the process of contributing data to the whole ecosystem of generating the data in the first place, the modeling that maybe comes downstream, I think that would really help make this more of a cohesive ecosystem.
Yeah, I would volunteer a number of folks. I mean, both of these folks run experiments, so they would be great people to beta test things down the road. So
That's great. So maybe one of you can drop me an email and introduce yourselves. And
he has a funny accent, so I'll let him do it.
Yeah, I could do that.
Yeah, brilliant.
Yeah, awesome.
Thanks, Matt.
Yeah. So this sort of spreadsheet enumeration is one of the main ways that we get to make these data sets that end up with dozens or hundreds or thousands of reactions, because they're not going to define those each by hand one by one. Now, because this audience is full of expert Python coders, or people who are interested at least in learning Python and figuring out the way they can bring Python into their workflows, I also wanted to mention that you can sort of, if you'd like, forget spreadsheets, forget the graphical interface, and go directly to defining these data programmatically. And so we have a number of different example Jupyter notebooks in the ORD schema repo that talk about ways of doing this and show some examples. And so, this one example is from org_syn. As you can imagine, there's a lot of detail that's involved in an org_syn entry. And so it sort of exposes a lot of different information about the schema. So, here the first reaction in the entry, or in the org_syn paper, it's running a 500 ml single necked flask, so we can define that. The vessel was oven dried, purged, and it has rubber septum. We can record all these preparations, attachments, details, and you can sort of see this, Pythonic way of defining different aspects of the reaction setup, what components are part of it, etc. So I'm not going to go through this in huge detail, but we've got these examples again in the ORD schema repo. Maybe we'll just throw this one in particular in the chat. This sort of can show you what potentially a fully programmatic way of defining a reaction with different outcomes and analyses looks like. Now, most of the data sets that we have are not just single reactions, but they are, again, sort of more combinatorial data sets, or high throughput or medium throughput screening results. And so we also have our examples that fit that. So many of us are familiar, right, with the sort of CN coupling data set from Onoman et al., from Abby's group. And so in this example notebook, what we do, the sort of strategy for defining this data programmatically, is sort of like the spreadsheet. So what we do is we define a single sort of prototypical reaction. So we say, okay, we're doing, liquid Harvick amination. We define all the sort of stock solutions that are used as different inputs. We define the sort of use of automation. We define the temperature control, pressure control, sort of the outcomes and the yields, et cetera. So we define one prototypical reaction through this programmatic sort of way. And again, I'll throw this in the chat. I know this is sort of a lot and it looks really intimidating. The first time you define a data set, it's slow and it's kind of painful, but then the second time, it's much more natural. And so it does only take sort of one or two examples to get used to this. Okay, so in this programmatic way of defining the full enumerated data set, we define this single prototypical reaction. We can print it out, we can inspect it, all of the fields that we've just defined about, what are all the inputs used, what are the components, how to run the reaction, et cetera. And what we can then do is we can pull the CSV that's associated with the publication. So, from a Jupyter notebook or from Python, right, we can import that data. So here, this gives us a list of about 4,000 reactions. There's 6 columns that are varied here. we've got some helper functions to help us resolve names to smile strings for this particular data set. But then essentially what we do is at the end of the day, we create a for loop and we just loop over all of our different reactions. And so for each of those 4,000 entries, we customize the reaction that we're trying to define. And we sort of save it to this running list. And that running list of reactions is what comprises then the data set in the end. So again, there's a lot of detail here that are in these examples, but what I want you to sort of mostly take away is that we are talking about defining data sets of reactions either one at a time through the graphical interface, or fully programmatically through Python, or with this sort of spreadsheet plus templates enumeration strategy. And we would be very glad to walk you through and help facilitate sort of the definition for any data sets that you've recently published or have, on the roadmap coming up. We can sort of step through the process, work on it together, and also work on the sort of contribution and review process together as well. Because there is a lot of complexity associated with the schema. And I'll put that schema link just in the chat, maybe as a final note, which is that if you do want to sort of inspect all the possible different fields and data and information you could define and record for a given reaction, this sort of protocol buffer schema file has it all. But again, this is more complexity than most reactions will require. So maybe I'll stop sharing and yeah, glad to sort of discuss any more. Or again, if you have data sets that are candidates for contributions, definitely let us know and we'd be glad to walk through them together.